All right, today we're pulling back the curtain on AI. We're not just talking about what it does, we're going to look at the actual blueprints, the core architectures that let a machine see a photo, understand a sentence, or even, create a stunning piece of art from scratch. So, how does this all actually work? I mean, really, how? It's definitely not some single magical black box. The truth is, modern AI is more like a whole collection of specialized tools. Each one is expertly designed for a very specific job. And the real secret, the key to all of it, lies in their architecture. And really, the key to understanding these architectures comes down to one big idea: inductive bias. It sounds complicated, but it's not. All it means is a built-in assumption. Think about it. If your job is to hammer a nail, you don't start from a random lump of metal and hope for the best, right? No, you start with a hammer. AI architectures are exactly like that. They're pre-built with the right shape, the right assumptions for the kind of data they're going to tackle. Okay, so with that idea in mind, let's meet our first specialists. These are the foundational architectures, the ones built to handle the two most common kinds of data out there: things we see, like images, and things that come in a specific order, like sentences. So you've got two major players here. On one side, you have convolutional neural networks, or CNNs for short. They're designed for grid-like data, the pixels that make up an image. And on the other side, you have recurrent neural networks, or RNNs, which are all about handling data that comes in a sequence, like words in a sentence. And their core ideas couldn't be more different. CNNs are all about understanding space, while RNNs are all about understanding time. So how do these vision experts, these CNNs, actually see? Well, it's kind of genius, really. Instead of having to learn what an eye looks like in every possible part of an image, they use one small filter and just slide it across the whole picture. This means if it learns to spot a cat's ear in the top left corner, it automatically knows what a cat's ear looks like in the bottom right. That property is called translation equivariance, and it saves an absolutely massive amount of work. But there was a problem, a big one. For years, researchers kept hitting this wall. They knew deeper networks could learn more complex things, but they just couldn't build them. Why? Because of something called the vanishing gradient problem. The signal that tells the network how to learn had to travel backward through all the layers. And with each layer, it got weaker and weaker, until, poof, it just fizzled out to nothing. The earliest layers were left completely in the dark, unable to learn a thing. And then came the solution, and man, was it clever. ResNet introduced this radical yet simple idea: the skip connection. It's literally an information superhighway. It lets the learning signal just leapfrog over layers and travel directly to the beginning. You see the formula there. That simple plus X, just adding the original input back in, was the whole trick. That simple addition created an express lane for information, and it completely unlocked our ability to train mind-bogglingly deep networks. It was an absolute game changer. All right, so let's switch gears and talk about the sequence specialists, the RNNs. For a while, they were the go-to for anything in an order, but they had a couple of, let's be honest, crippling flaws. First, they were painfully slow because they had to read everything one word at a time. And second, they had a terrible memory. They'd often forget what the beginning of a long sentence was even about by the time they reached the end. So how do you fix a bad memory? Well, you bring in the LSTM, the long short-term memory network. The genius of the LSTM is its cell state. Just imagine a separate conveyor belt running alongside the main assembly line. This belt is the network's long-term memory, and it has these special gates that can open and close, giving the network total control over what crucial information to keep on the belt, what old stuff to throw away, and what to use right now. It was the perfect fix for that pesky memory problem. Okay, so LSTMs fixed the memory problem, but that whole one word at a time thing, it was still a massive bottleneck. The entire field was kind of stuck in first gear. They needed something revolutionary, something that could just break the whole sequence wide open. And that's exactly what happened next. And here it is, the transformer. This architecture did something that, at the time, was totally wild. It just threw out the whole idea of going in order. It abandoned recurrence. Instead of reading word by word, it developed an incredible new mechanism that let it look at the entire sentence all at once. And that mechanism was called attention. So how on earth does that work? Well, you can actually think of it like a conversation happening inside the sentence. For every single word, it creates a query, which is like the word asking, to understand my role here, what context do I need? Then every other word in the sentence holds up a key, basically saying, hey, here's the kind of information I represent. The original word then finds the most relevant keys and tells those words, okay, you're important, give me your value, your actual substance. It's this constant parallel Q&A that lets the model build a rich understanding of the whole sentence instantly. Now, this incredible power, it doesn't come for free. Not at all. Because every single word has to check in with every other single word, the amount of computation doesn't just grow, it explodes. This is what we call quadratic complexity, and it created a massive roadblock. Honestly, today's huge language models wouldn't even be feasible without some really clever engineering fixes, like an algorithm called flash attention, which completely rethought how the model talks to memory to make this whole process workable. Okay, so we've looked at how AI learns to understand stuff, to see images, to read text. But now let's get to the really fun part. How do we take these ideas and build architectures that can actually create new things from scratch? Welcome to the world of generative AI. When it comes to making new stuff, there are basically three big schools of thought. You've got GANs, which are like a constant game of cat and mouse. You have VAEs, which are like expert map makers. And then you have diffusion models, which, believe it or not, create things by first learning how to destroy them. Each one is a totally different way of thinking, and each comes with its own unique challenges. GANs are just so cool. It's literally a competition, an adversarial game between two networks. You have one network, the generator, that's like a master art forger. Its only job is to create fakes that look real. And then you have another network, the discriminator, that's the detective, whose only job is to spot those fakes. They go back and forth, training each other, getting better and better. But the big problem here is something called mode collapse. That's when the forger finds one single fake that always fools the detective and just starts making that same thing over and over and over again. All the creativity is just gone. VAEs take a completely different, a more philosophical approach. Their goal isn't to trick anyone, it's to learn a really, really good map of the data, what's called a latent space. They learn to compress an image down to a single point on this map and then decode it back. The idea is if your map is smooth and well organized, you can just pick a random spot on it, any spot, and decode it into a brand new, totally valid image. For the longest time, this was just a neat theory, until a little mathematical innovation called the reparameterization trick came along and finally made them trainable. And that brings us to the current king of the hell, diffusion models. The way these work is, well, it's beautifully backward. First, you take a perfect, clean image, and you just destroy it. You gradually add random noise, step by step, until it's nothing but static. That's the easy part. Then comes the hard part. You train a massive neural network to learn how to undo that process, to look at a noisy image and predict exactly what noise was added. Once it gets really good at that, well, to create something new, you just hand it a screen full of pure static and say, go, undo it, and out pops a masterpiece. Now, you might be thinking, doing that whole noise and denoise dance on a huge high-res image sounds incredibly slow, and you'd be right, it is. So here's the brilliant hack that makes models like Stable Diffusion practical. They combine ideas. They use a VAE-like model to first squish that big image down into a tiny, tiny little compressed version of itself, the latent space. Then they run the entire diffusion process in that small, fast space. Only at the very, very end do they decode it back into a full-sized image. It's a genius move for efficiency. So when you step back and look at this whole journey, it's pretty incredible, isn't it? We've gone from architectures that learn to see objects in space to ones that understand the flow of language through time, all the way to models that can literally create new worlds by reversing chaos. These aren't just random algorithms. They are deep, clever blueprints built on fundamental assumptions about our world, about how we see, how we communicate, and how we create. They're learning to mimic our own cognitive processes. And it just makes you wonder, what fundamental process of our reality will the next generation of AI learn to master next?